Yeah, this is meant to be a conversation, really. This is for information back and forth. I find most people learn best in conversation as opposed to some jerk on the stage being like, do it this way, right? So please ask and answer as best and as often as you like. I'd rather have good conversation than get through a certain set of slides. Fair enough? Bathrooms, back over that way, if anybody's interested. We got parking taken care of, food in the back. Don't worry about getting up and doing your thing, whatever. We're here for everybody's benefit. So that said, I've had a bunch of certifications. I've let them all go because I worked for Mitsubishi for 5.5 years. I didn't need it. But now I'm getting back into, actually for 1.5 years, I was a partner in an HVAC installation company, heat pump installation company, building out the technology, building out the relationships so that people understood the technology and how to apply it properly. And more recently, I had an opportunity to join another friend in a consulting company called Point 6, and our goal is to help people build verifiably better homes, right? So filling that gap between design and installation and verification and make sure that what was intended by the owner is what's delivered at the end of it. So that said, let me turn that back on. Questions, things we're gonna talk about. I've got a number of things up here, but really it's talking about cold climate, it's talking about applications of the technology. It's talking, if we're focusing on residential HVAC, but we are going to be, and I apologize I didn't change that title there, or that one bullet point. We're going to be talking about air to water as well along the way, because I know that is a key interest in this market, and there's some, I won't say cons, but there's some limitations currently right now with some of the technology, but we're seeing some pretty impressive movement on that. So why heat pumps, do they work in this area, et cetera. Costs and backup heat and these kinds of things. So I'm gonna start sort of big picture real quick, and maybe you've seen this slide before, but I like starting with it because it frames the problem from my perspective pretty well. That is the energy use in the United States, the US economy for 2023. We don't have a 24 number yet. We might not get a 24 number for the next few years. We'll see how that plays out. But that red box up there, that's electricity generation. We're going to be talking about that a little bit. But more importantly, I'm focusing on those numbers on the right-hand side, right? If you look at how those play out, we waste 2/3 of the energy we pump into the US economy, either by sound or heat or whatever, but it's not put into service. It is rejected energy, right? So 33%, 34% is pretty good. Batting .330 will get you into the major leagues, possibly into the World Series, et cetera, right? I think we can do better when it comes to energy use across the entire US economy. And that quadrillion BTUs, those quads, one quad is 264 years of a gallon of gas burned every second, right? So a gallon of gas burned every second for 264 years, that's one quad, and we do that almost 100 times. So that's 25,000 years worth of gas being burned like that, and we do that every year as the US economy. Okay, that's fine. I just think that we can do better when it comes to the efficiency of that. And part of the way that we get there is building codes, right? Making buildings more efficient. And you can see that long trajectory from the 70s into the 80s, 90s, 2000s and such. But we really started paying attention right around that 2006, 2009 timeframe, where the envelope of the house, as well as the systems in the house, started to get significantly better, pushing towards that net zero goal down on the bottom right, that maybe we hit it, maybe we don't. What does it really look like? I think the key there is that right about that, where it says carbon savings potential, right about where we're at with 2024, we're at a pretty good envelope position right now just in code. And now we can start to look at renewables. Now we can look at power provided, whether it be on-site or through the utility companies, being more how we collect it rather than burning 60, 70 million year old sunlight, we can use today's sunlight, right? We just short cycle that circuit from however long ago to the past 24 hours, right? And that's how we get down to that bottom right-hand side. Now, builders looking at not just the envelope, but looking at this transition to all electric. This survey was done by Green Builder Media. It's a lot of consumers, a lot of builders, 1,800 builders in this survey. And consumers, would you buy an all-electric home? Mostly yes, or maybe unsure. I don't know, tell me more. Builders, would you sell an all-electric home? Mostly yes, certainly unsure. Very few are in that no category, being concerned about whatever it is they're concerned about, and that's fine. I'm not here to tell somebody that they have to do something. I'm here to say, let's talk about how to do it. Now, of those all-electric homes, would the homeowner invest in an all-electric item, right? What would you invest for an all-electric in your home? And the number one item out there is heat pump heating and heat pump cooling, right? As well as heat pump water heaters and on down the line. But we're going to be talking about those top items today. But clearly a top item of interest for the consumers and the builders. So this kind of interest, this kind of movement in the industry, we're seeing that movement with AHRI is the American Heating and Refrigeration Institute, and that is, those folks track how many pieces of equipment get sold every year in the US. So you can see that graph. The blue line is air conditioning, the dotted gray line is furnaces, and the orange line is heat pumps. Clearly heat pumps it's on the move. The race really is between heat pumps and air conditioners, but what does a heat pump do other than just heat? It also cools, right? It can do both. So eventually the heat pump is going to take over both functions, if you will, as we go into the future. So, and I certainly wouldn't want to be in the furnace industry right now, given that it is seeing a significant decline, and I'm seeing people leaving the industry and going into heat pumps deliberately. So when we look at heat pumps, whether it's space heating, water heating, space cooling, etc., we add those things up. We're talking about the lion's share of energy used in most homes. This is a national graphic, so it's not that it applies to this location, because we see a lot more heating in this climate for sure, but it just sort of gives a frame of reference for how much heating, how much cooling, how much in appliances, and etc. By the way, you guys everybody's familiar with what a HERS rating is? Right? Okay, so nodding yes. That other down on the bottom, that 28%, that's stuff that's not showing up in the HERS rating. So when the energy use shows up on the utility bill and it's different than what the HERS rating says, that's a big reason why, right? So when we look at the energy use, the lion's share being in the heating and cooling and the water heating, we can also think, let's move towards all electric. Well, what are the utilities doing about this? I know this is really small, sorry for the eye chart, but I just wanted to sort of throw up all the possible utilities depending on where this is being seen at. So I'll get in over here. Sorry for the camera, I don't know if you can still see me or not, but Excel being the largest segment, the largest ratepayer base in the state of Colorado, more than 50%. They are 42% renewables in 2024. They're already there, right? And they're heading towards 80% greenhouse gas reduction by 2030, and 100% by 2050. So that's where you all are at here in Summit County, for example. But you might have clients or customers that are further out, Tri-State or Holy Cross or others. All of these companies, all of these utility companies, whether they're utility, investor-owned utilities or rural electric, et cetera, they're all moving in this direction and significant reduction in greenhouse gas emissions. So they're changing the power mix, and I would arguably say we're halfway there.
What's the difference between renewable and net zero?
Right. It is a great question, and please chime in if you all have if I'm don't answer this well. Renewables are sort of this direct supply of power, right? It's the wind, it's the solar, it's the hydro that's in the mountains up the mountain from Georgetown, etc. That is the renewables, and then there's storage for for storing that. You know, you're nodding yes because you're asking me a loaded question here. The net zero is how do we offset that, right? So how do we use power to pump water back up in that hydro and say, well, we're going to use that power from a power plant or from wind in the middle of the night and then push that back up when our loads are low, and then we're going to use that stored energy when our loads are higher. So there's credits going on with a lot of that. That's part of the net zero, but then there's also different ways to sequester the carbon or the emissions that are released, etc. So we're sort of taking credit from one and applying it to the other, and that's how they're looking at that net net greenhouse gas reduction.
Shawn, can I add something?
Yeah, and even nuclear is evolving as well. So that's new technology piece. There are new versions of nuclear that are actually being fueled by nuclear waste that we used 30, 40, 50 years ago or from another part of the planet. So does that help? Yeah. Cool. I'm a volunteer with Go Electric, that top right corner logo there. I volunteer with this organization, and they're sort of neighbors helping neighbors on these topics. They put together some slides, so I'm going to have some different looking slides in here. But they are motivating people and helping people understand how to go all electric, how to go net zero, etc. And so their key points are, hey, electrify everything you can and then switch to renewable energy. Cool, simple message. And on the right-hand side, there's a bunch of things that people have done to their homes typically over time, whether it's light bulbs or whether it's appliances or whether it's air insulation and air sealing. But now we're getting into some of the bigger stuff. Certainly windows are always a consideration, like, oh, I want new windows because something broke, or these are loud, or they're ugly, or whatever. There's motivations for that. But when it comes to replacing a furnace with a heat pump, that's not necessarily a natural progression of technology, right? So heat pump space heating, heat pump water heating, and then induction stoves, and I think a lot of people would agree that natural gas stoves, you got to cook with gas, and this is sort of this holdover perception. And it is great, and the technology on induction is getting way better. If you like cooking with gas, do yourself a favor and either definitely do or definitely don't look at the indoor air quality impacts on the health with particulate matter, which is a consideration, particularly for people that happen to care about their kids or happen to care about their aging parent that's in the house or what have you, because these things are not great. So moving on with that, electric home, these are just sort of a visual representation of those different ideas that we talked about. And whether or not you have solar on the roof, by the way, because the utilities are already at that 40, approaching 50% renewable, I would say putting solar on your roof is sort of a wash. I would actually say, whatever it is, 10,000, 20,000, something like that, I'd actually invest in improving the house a bit and then potentially putting a battery in so that you can be a little bit more resilient. Or maybe putting in and I know Jess doesn't love this idea, but I'm a fan of sort of this off-grid capable and a propane generator, right? So if you've got a tank, putting in a good generator so that it generates electricity to run your house indefinitely, and you're only filling it up once every 2 or 3 years because you just don't use that much propane, and it's truly a backup energy storage, right? So a consideration. Benefits of heat pumps. Who lives with or works with a heat pump on a regular basis? Yep. What do you find? What's the benefit to you for heat pumps? A little bit of defrost in there. We'll talk about some of the downsides, and certainly less efficient when it's colder. We'll talk about that as well. But I would say, now that you've had a heat pump, would you say, no, I'm going to get rid of the heat pump and go back to what I had before? No. Okay. We'll talk more about that too. Drawbacks. It can be costly, right? This is expensive technology, and if you want to do it when you're ready to do it, go for it. But most people start to look at this technology when it's time to replace their existing equipment, right? Now you're saying, oh, is it 15 grand to replace, to step up to a way better furnace, or is it 20 grand to step up to a heat pump? Now I'm using Denver numbers because it's way more expensive up here, and that's just the cost of living up in the mountains, and we all know that it's higher cost of real estate, it's further drives, et cetera, so on, and it's just a different market. Less efficient and more expensive to run at very low temperatures, right? So we'll talk more about that strategies-wise. Supplemental heating may be needed, and depends on how you size it, depends on what you need for your house, et cetera, but having a backup plan is probably a pretty good idea in this climate. And needing to find an experienced installer. One of the greatest pain points I think that High Country Conservation Center experiences. Who knows a really good heat pump installer?
He's sitting right there.
Which one is he? Oh, that's right. What company are you with? PSM?
It's my company.
Nice. Sweet, man. We got to chat later. I might take you to lunch. Excellent. So heat pump water heaters, I stuck this slide in because I think it's an important piece of this transition. And frankly, heat pump water heaters are just self-contained pieces that do a great job. They are cost effective almost out of the gate. They are quiet as well, although they do make a little bit more noise. It's sort of like maybe when they run, sort of like maybe a noisy refrigerator. But they, 3 to 6 times more efficient than gas. And in fact, that 6 times, if you can provide a little bit of warmth to that space, if you've got another heating system, if you've got a warm area of the house, maybe a sunny spot, maybe something that's next to your mechanical room that already has some heat, that's when that efficiency goes up. And I've gotten that directly from the engineers at Rheem. They say, if you can provide 90-degree air to that device, you're going to be 600% efficient. Bonkers. It's awesome. Love it. Tends to pay for itself fairly quickly, sized correctly for usage, and part of that can be the mixing valve that you put in. So if you keep the tank at 130, 140, but you dial back the mixing valve to deliver at 120, you've actually just extended the capacity of that tank by about 30%, something like that, right? And then what to do with that cold air that's coming out the right-hand side there. I'm a fan of ducting that into the crawl space if you can, because your crawl space is already cool and it might be a little bit damp. You're saying no, maybe no. The heat pump water heater dries the air out. So that cold air that's coming out is actually drier. So it's thirsty. It's going to absorb moisture out of that crawl space. Then the question is, what's your return air path? So if your crawl space is super nasty and it's going to be leaving anyway, because it's probably really leaky, etc., no big deal. Not ideal, but ideally, you want to put in that vapor barrier, insulate the foundation walls, bring that crawl space in to be that coupling between the house that's at 70 and the ground that's at 50 or 40 or 30 or whatever. But you don't want that space in between to be 0, right? So improving the crawl space, bringing it into the conditioned space, provide the air that's coming out of the water heater into that space that's dry, pick up any extra moisture, and return it back into that, basically back to that intake vent, back to the conditioned space. And as long as you're filtering and managing air quality in the house, you're good to go. Does that help a little bit? I'm happy to chat more. Yeah, you're using the crawl space as a tempering space, basically. Yeah, and that air going out is going to help dry out that crawl space. We'll talk more. All right, so it says geothermal up here. I forgot to change it. Geothermal is what they have in Iceland, right? These are 5,000-foot wells that come out as steam. Ground source is really what we're talking about. GSHP, ground source heat pumps. And so they just go down, whether it's horizontal or vertical loops or whatever, a few hundred feet of loops that help pick up heat and deliver it into the house. efficiently. That's the source energy, if you will, for these heat pumps. So that ground is a relatively consistent temperature throughout the winter, and you've got to do boring. You either have to do a lot of site work to remove soil to do a horizontal loop, or you got to drill down probably a few loops to be able to handle the capacity needed for the house. But it is the most efficient space heating option that we have available today. You've got efficiencies in the 300, 400, 500, 600%, depending on the condition that you have under the ground. I would avoid very dry ground with this, because when it's very dry, you're going to pull out more heat from that ground loop array than you can put back in the summer. Because there's a lot of ground. If it's very dry, you're effectively going to overdraw heat from that ground because it gets replaced in dry ground fairly slowly. If you've got fairly wet ground, that's a great opportunity because that heat is transient. So within a fairly short amount of time, I'd be guessing at how long, because it depends on how long. But if you've got wet ground, that heat's going to be replaced regularly, and you probably won't be overdrawing that loop field throughout the season. Yeah, but if you're doing new construction, it's a great opportunity to maybe look at a horizontal loop or something like that, potentially under, especially if you've got a heated driveway. Put your ground source underneath your heated driveway, you're actually sort of recouping. That's actually energy recovery, if you will, off that 2 million BTU boiler that you just put in or whatever. You know, I'm not getting into, heated driveways any more than that today. But what do people really want? What are they really looking for? They're looking for the basics, right? They want to be comfortable. They want to be safe. They want it clean. They want it efficient. They want it reliable and cost effective, right? This is really what it boils down to for the homeowner. And I think all of us being homeowners, we want this for ourselves as well, not only for our clients, but for ourselves. So we owe it to ourselves to dig in more deeply on these things. Here's another little side note that I found as well. It actually can be reflective. Heat pumps can actually reflect a higher selling price for the home if you have somebody that understands it, whether it's being the appraiser or the real estate agent, getting it into the green fields that are potentially in the real estate market that you're in. These are all considerations, but the potential is there. All right, so this is my house, and I wanted to just make it relevant because I've hacked my own life with all these things, right? I've put myself through the rigor of going all electric. So I've insulated, I've air sealed, I've changed out my windows. Those were basically due to comfort and functionality. I've electrified everything in the house. I have renewable energy on the roof. The solar panels in the back, they cover 3.5 kW, which is only about a quarter of my annual energy use. So it's just a portion. And then power management. On that top left, you see my power display on my app. That's my phone app, right? So Emporia is that product. There's an image of it right there. I don't represent Emporia, I just think it's a really good product, and it's based in Colorado, so that's a win. My point is that for about $2,000 a year net, right, after solar and all that stuff, I run my whole house and drive about 23,000 miles a year for $2,000, all in. Add in my cost of infrastructure, if you will, solar. That was another $100 a month for my loan that I just paid off, right? So that was 10 years on that. So I'm actually netting about $300, $400, $500 a year, depending on price of energy, et cetera, and so on, right? And that's just, that 2,000 is a reflection of the efficiency of the house, and I still pay a utility bill, but I'm invisible to the grid in the summer because even though my 25% capacity heat solar is not everything I need for the overall year, it is enough for me to be invisible to the grid. I actually can overproduce during the middle of the day when it's 95, 97 degrees outside. So I'll take that as a win as well. And we're happy to chat more about that if you want to. So we're going to dig in straight into heat pumps going forward. We're going to get far more geeky. And we're not talking about these heat pumps, right? So the photo is an ex-colleague of mine, Henry. He's an outstanding technician, and Colorado Sun did a little story about this one. But this, the quote here is, on December 22nd, a few years ago, it was -18, and the homeowner says, quote, "Overall, it was just another day. It was not much of an event." They work, did the job. Do the math, size it right, install it right, does the job. So when we think about things that are in our lives, we have heat pumps already. You have a refrigerator. It's a heat pump. It's pumping heat out of the box. You might have an air conditioner, maybe not up in this market, but maybe you do. That's a heat pump. It just happens to be running one direction. It's pumping heat out of the house in the summer. You've got this zoning. You might have zoning in your heating system, but you also have this sort of zoning in your car, right? You've got this passenger side, driver's side, front and back, et cetera, and so on. So people are used to this concept of zoning. And then who's willing to give up their variable speed drill for a single speed drill? No way. I will never give up my spirit. I would never make that trade. That's a terrible trade. That's moving backwards, right? So once you have this technology, you don't want to move backwards. You wouldn't leave it. And it's more efficient. And this is a nice little graphic of why it's more efficient. It starts up, and then it sort of settles back and maintains, that orange line. That inverter compressor, that's really the key, is that this inverter compressor turns on, and it puts in enough power to deliver heat and then settles back and to maintain that at steady state, we might say, right? As opposed to the gray line, which is this on-off, on-off, on-off scenario. And it's not that on-off is bad, but it is less efficient in this application because we want to be able to, we're saving energy in the gap, but we're using more energy in that peak. And the utility companies are particularly interested in those peaks, right? They want to know that those peaks are spread out or limited as best we can so that they can continue to deliver power reliably. Oops, wrong way. And so that's where the energy savings comes from when the system has a chance to turn on and run consistently over time. This is hard to read, I apologize. I just thought it was a really fun graphic. A guy from NREL put it out recently, and it's on LinkedIn. He hasn't really published it, so I don't have a great photo of it. But it sort of lays out the landscape of heat pumps all over the place. Left side is air source, middle is ground source, water source, waste heat, boilers. Right-hand side is more sort of commercial grade. The left-hand side is more residential grade. And then the type of technology of the heat pump cycle, et cetera. We're talking about what's in that red box there. And that's single zone mini splits, which could be a great solution for an existing house on a remodel that's saying, hey, we're actually pretty comfortable in this house. We just want to do something that's a little bit better. Great, put in a cold climate single zone wall cassette or ceiling cassette and knock off 30, 40, 50, 60%, maybe even 70% of your heating load, depending on the sizing and the layout of the house and all that stuff. The multi-zone, that's these mini splits. In every room, you get a mini split and you get a mini split. Well, actually don't do that. It's not recommended for various reasons, but multi-zone could be ducted in one spot, ductless in another spot. Maybe on the water side, it could be zoning of, what you're used to already in hydronic zoning. That would be that multi-zone scenario, maybe. And then hydronic, that could be, you can actually, there's systems out there that can say, we're going to heat the floors in the winter, and then we're going to have an air side, air conditioning in the summer. It's the same outdoor piece of equipment, and it just switches, depending on the day or the season. So there's ducted. We don't have to spend a lot of time on that, There's ductless. We don't have to spend a lot of time on that. And then hydronic, which I think most people are interested in here. And by the way, hydronic can be delivered by ducted and ductless methods. So it depends on the house, depends on the remodel, depends on the goals, depends on your air quality scenario. If you can integrate air quality into ducted systems, that's a great way to go as well. So here's a nice range of manufacturers. I got this from my good friend Dan Wildenhouse. Rest in peace, Dan. And so he talks about air-to-water heat pumps primarily for space heating. Some can do that cooling side, and some can do domestic hot water. And so here's a basic layout of not only the the outdoor unit connecting to the indoor units, right? So here's your domestic hot, here's your heating in the floor, and then these various smart devices or uplinks to management or connection to the photovoltaic. So there's actually, opportunities to say, well, I've got more solar right now, so I'm going to preheat or pre-cool my house or what have you. And then interconnection back to the grid potentially. So this type of technology really sets up this great opportunity to not only manage costs and improve comfort, but actually utilize the utility company as a partner in drastically changing what you pay for your energy, how it's managed, but potentially this two-way exchange of energy back and forth if you've got solar and batteries and preheating and thermal storage and these kinds of things. It's pretty interesting stuff. So who's curious? How the heck do heat pumps work? It's okay. Raise your hand. Everybody knows. Everybody knows how they work.
Thought they were magic.
They are magic. Magical anyway. Right. Magic's fun. I like a good magic. What do they call it? Up close magic? Yeah. Nailed it. Yeah, so I'm going to start off by framing heat pumps in hopefully a useful way. Heat pumps come in different capabilities. There's roughly 3 different capabilities represented here in this chart. The NEEP Cold Climate List, that's that logo on the top right there, and they focus on that 100% capacity and 70% capacity cold climate heat pumps. The blue line is that old photo that we saw, that crazy, these old heat pumps. They're not bad heat pumps, honestly. They're not bad. They're just designed for a different part of the country, right? They're designed for the warm smile of the US, where it's comfortable most of the year. And sometimes, bless you, sometimes you're hot and sometimes you're a little cold. That's fine. That's not what we're talking about. We're talking about either the yellow line at 70% capacity at 5. Does it get colder than 5 degrees around here? Does it stay colder than 5 degrees around here? Is it okay that we not worry about those right now today? Great. We're going to focus on that 100% capable at 5 type of system, which is a small segment of what's listed on NEEP. There's, I think, more than 130,000 matchups on NEEP. That's a lot of different systems to pick from. How do you pick the right one? Well, first off, ignore the 70%. And then second, look at that 100% capable for your location and how you design to and how you select that piece of equipment. So Climate Zone 5 plus. Is everybody comfortable with the climate zone metric? Okay. So now when we talk about up in the mountains, really cold for long periods of time, we think about, okay, do we need to add in extra heat? Supplemental heat, I would suggest to you, is extra heat. Not instead of heat, just on top of what you already have. The heat pump's still running, the supplemental heat is additional. Backup heat is a switchover. The heat pump turns off, and now you've got this other system heating the house. And that's depends on the house, depends on the setup. Both are valid, depends on what you've got. Cold climate air source heat pump specs. We're going to spend some time in this arena for a little bit here. So the top chart is 100% capacity at 5. It was that red line we saw. So that red line you see across the top, that's the capacity of the heat pump represented in that chart. The line that you see sloping down to the right, high on the left, low on the right, that's the heat load of the house. Is everybody, if I say heat load of the house, is everybody comfortable with that? Okay. So the colder it gets, the higher the heating load goes. We're not really worried about heating the house at 50 degrees, maybe a little bit, but not really. What we're really worried about is those cold temperatures. Now, this chart, and I apologize, I should have pulled up this chart for this area. This is Denver, but because your chart's going to look more skewed to the left, right? You're going to have more hours in the year. Those blue lines that you see, those are sort of what they call bins of hours. So I would say on this area, you're probably going to see something about like that, right? Because you get cold here, but what's the coldest it gets? Quiz.
30 below. Man.
When was the last time it was?
It's probably been 15, 20 years.
15, 20 years. And for how long? Right? For how many hours? Yeah. I looked up recently, I think there was something saying, oh, it was negative, I think, 16 or 17 for like a 12-hour period, and that was the worst it had been for decades, right? So it'll get really cold, but keep in mind, we're not talking wind chill. We're talking actual thermostat readings. Wind chill is irrelevant to heat pumps. They don't care. You know why they don't care? Because they don't sweat. We care because we give off moisture from our skin. That's wind chill. The next, on the bottom half here, this is at 70% capable, and you can see these gray areas up in here. That's that supplemental heat, or potentially backup heat if that system stops. But this is a lot more supplemental heat. This is a much larger supplemental heating system that you have to pay for, either to install it, well, both to install it and to run it. So that's why I would say focus on the 100% capable, not the 70% capable. Need supplemental, yeah, so this is a great project. This is not in Summit County, it's up above Idaho Springs, but it's about 10.5 elevation, down in a valley, so it gets a cold air just running right down past that guy. And they opted to do heat pumps for this, and that's actually going to be an Airbnb. So they've got people staying there, year round, and it took them a while to get comfortable with this idea. And they've just got little plug-in heaters that they give to people to say, oh, by the way, if it gets a little too cold in here, plug this in, turn it on, and then when the place changes over, Airbnb-wise, they just unplug it, wire it back up, and they're completely code compliant and rental permit requirement, all that stuff. So just thinking about the belt and suspenders, right? So the suspenders are that just in case in addition to the belt. So what about backup heat? Well, in Fargo, actually we can skip this. This just says that heat pumps work when it's really cold. That's all it really says in Fargo. Actually, I will say that the key point on this is that the backup capacity that was only needed for 5% of the year in Fargo, North Dakota, right? Yes, there's backup. Yes, there's energy needed. Yes, the system needed to call for that assistance, but it wasn't a huge impact on the utility bill. Maybe 5% of the year, maybe a 7 or 10% impact in the utility bill, something along those lines for that area, but an interesting consideration. So how do heat pumps work mechanically? We're going to get more into that. I describe it as a pulley or a lever, right? So how do we lift more than we can physically lift? Well, we use engineering, right? We use a pulley instead of applying, like, this isn't a bad way to go because you're supporting that weight, but you're still applying 150 pounds of force, right? You still have to apply that force to lift that 150 pounds. Well, a heat pump is more like an actual pulley system where you've got 2 pulleys, and so you're applying half as much to lift that load. Or an even more engineered system with 3 pulleys. and you're applying a third as much. And you can go further and so on. You can go into that fourth pulley and apply 25%. Diminishing returns, of course, and complexity and all that stuff. But that's fundamentally how a heat pump works, right? So 200%, 300% efficient, this is what we're talking about. And the chart, or the little icon up on the top right, the output versus input, that's coefficient of performance, COP. Coefficient of performance is input over output. Sorry, output over input. Output over input. So even though the input looks like it's a lot more, you're only applying 50 pounds here, and you're lifting 150 over there, right? That's the lever. So remember that COP. We're going to use that again. So the physics of a heat pump functionality is phase change. They use a refrigerant that is a vapor that turns into a vapor. It boils at about -50, -60, something like that. So that vapor is then put into a system, and the pressure is managed. We're managing the temperature and pressure of the refrigerant around its boiling point. That's all we're really doing. And so we're using this giant block of hidden heat, if you will. That's water, like steam. We've built our civilization on steam, literally. Our entire human existence today has been entirely dependent on the use and application of steam and, to a lesser extent, ice. It's just phase change. That's all we're dealing with. So the heat pump compresses that refrigerant, and well, actually, let's step back further. It takes the refrigerant from the outside. All it has to do is get the refrigerant colder than outside. That's the number one thing. If the refrigerant is colder than outside, it can absorb heat from the outside air. Doesn't matter that it's -20, because this stuff boils at -50, right? So it absorbs heat as phase change, goes from liquid to vapor on the outside. And then that vapor gets compressed in the compressor here, and that temperature, now that it's absorbed this hidden heat, it's now being lifted in temperature from, say, -10 or -20, and it's being lifted in temperature up to, say, 130, 140, right? That's what the compressor does. So it adds in some heat for sure, but the magic capture of heat is outside in that boiling. Once it goes inside, that fan blows across that coil, and it blows across 130, 140, 150 degree coil and delivers that heat into the house. What's happening there is it's taking that vapor and condensing it back into a liquid, right? It's like, I'm going to have a bad example of this, so I'm going to skip it. All it's doing is taking vapor, turning it into a liquid, and that energy that was in that latent heat, that hidden heat, is delivered to the house, and you got liquid going back out. And that liquid goes through this expansion valve, and that's how it manages the return pressure, right? So it's changing from sort of this warm down to cold, because when you know those spray cans of, I think of like a keyboard, or when you have spray paint or something like that, where you release pressure and it gets cold. That's all that's doing. It's just relieving the pressure and lets the pressure drop down. And the heat pump is in control of how much these work. That's all it's really doing. And when it finds the right amount of control for this, it releases that pressure down below outdoor temperature again. And it's just a loop. And that refrigerant just goes through the loop like that. And it's pressurized and depressurized and pressurized and depressurized around the boiling point. And it's going from liquid to vapor to liquid to vapor to liquid to vapor. And that's how we capture heat from -20 degrees and put it into the house at 120 degrees. Right? Clear as mud, right? All right. So this is looking at the same basic chart in a different way. This is off of one of the technical documents. And the previous is like the general approach of how a heat pump has worked, how heat pumps work. This one has a little bit extra technology in it called a heat injection circuit. And what it's doing is actually being even more efficient about it. It's saying, well, I know I have, this is the indoor coil. I know I have a little extra heat that's leaving that didn't get used, because it might come in at 140 degrees. We might get 30, 40 degrees off that coil, and now it's about 90 degrees or something like that here. Well, it's going to take that. It's going to move through this expansion valve and separator, and it's going to separate the remaining liquid and vapor. And it's going to say, oh, well, I'm going to use this this liquid here that's colder than the vapor, and I'm going to extract even more heat from this. But I'm not delivering it into the house. I'm delivering it back into the system out here. So it's just capturing waste heat. That's all it's really doing. And there's other ways that modern high-performance cold climate heat pumps do that kind of thing. Is that helpful to go through those? It's geeky, but hopefully it's helpful. Cool. All right, so heat pump math. This is a system. Admittedly, it's not in Summit County because I don't have much data on Summit County ones. We're gonna have to talk. Yeah, exactly. So this is a system that's installed in Denver. This is a few years ago when it was negative 18 in December 22nd, and it was that cold snap. Well, this house is designed to the heat load on the house is around 0 degrees, and it was well past that. So when we design a heat pump for a house to heat it to maintain comfort at 0 degrees, but now we're negative 18, how do we keep that house comfortable, right? Well, this house somehow, magically, and we can get into it more later, it actually kept up. The system can keep up because there's things going on like thermal mass, right? How much does a house weigh? Hundreds of thousands of pounds. Well, as long as you can keep a good amount of heat going in that house, you can actually ride through these low points. And you all know what this is like because you feel it with the boilers you have. You know that a boiler heat is very different than a furnace heat. It just rides through those temperature swings, right? And so a heat pump like this, it's really just doing the same thing. It's just riding through because it's continuously providing heat. It's not that on-off scenario, right? So it's continuing to heat the floors and heat the couch and heat the drywall and heat the mass inside the thermal boundary. But what really stands out to me is that it did it at way below the rated energy use, right? So this top line, rated ampacity for this system is 42 amps. The average for this way below design condition was 23 amps. So it's using just a portion of the rated capacity. And it never went above 25 amps. So this is where the magic happens from the utilities perspective. Why is this technology so much better than this on-off single speed or maybe 2-speed systems that are like, imagine driving a car with 2 buttons. One pushes you at 60% power right now immediately, or the other is 100% power right now immediately. We don't drive that way. We have an accelerator pedal, and we can push on that pedal as much or as little as we need to, and we can slow down as much as little as we need to. We're already used to this technology. We just happen to be applying it to a different case, and that is our homes and our efficiency. So overall, top right corner, here's the math. 5,500 watts, watt hours average. That's over this one day. I couldn't drill down any further than this. This 132 average through the day because it was a cold day, and here's the weather for the day. 5,500 watt hours times BTUs per watt times 2 COP, which is approximately how this system was operating, and you're just gonna have to trust me on that number for right now. 37,500 BTUs per load. So actually, I'm gonna tie this back, and it gets super geeky here, but 37,000 BTUs in that condition, but wait, the heating load on the house was 46,000 BTUs. why are we so different? 46,000 BTUs is way more than 37,000, right? Well, that's sort of what manual JSD is doing to us. It's already overestimating. And in fact, I don't know who gathered that load calculation. I don't think it's a bad load calculation. I think it is just a load calculation that is commonly applied. And so now we have a little bit better clue as to why this system was able to handle negative 18 so easily, right? Does that sort of close the loop a little bit on you? Okay, so we'll go into more of that in a little bit. This is my house. So that all electric house with the car and all the stuff, I have a 100 amp panel. So I run my whole house on a 100 amp panel, which according to NEC is should be illegal, apparently. But not really, because there's actually a clause in NEC that says, oh, by the way, if you gather 15-minute data for a month, and you can demonstrate that you have the capacity on your panel to do this stuff, you're good to go. It's called an existing load study, right? And this 15 minutes over, they ask for it over a year in the code section. There's an exemption that says, oh, by the way, we'll take 30 days of it. That'll be okay. I did it for over 2 years. And during that 2 years, my absolute worst 15-minute data segment was 57 amps. What do you think of that? He's saying, yeah, I know. Does anybody pay attention to, I realize I'm off in the weeds on these things. But, right, so let's discuss with the very astute building officials that understand stuff that I don't understand. What does it look like if you know you've got a responsible, diligent designer, builder, architect, project team? What would it look like for them to say, hey, by the way, I know NEC says this, but we think we can do it with less? What would you need to see? Right. So you need a bit more forward-thinking engineer to say, yes, I agree with the math. Stamp.
We're talking residential, right?
No, that section, NEC 2287, applies to commercial as well. So I believe that the logic stands for commercial as well.
I think we're
So the comment from the building official, from one of the building officials, is that residential plans are typically not MEP engineered, but you would be looking at some additional supporting documentation from someone with a stamp. Would the architect's stamp be okay? If they included documentation within their stamp set, would that be acceptable? Okay, on commercial for sure. On the residential, if they don't have an actual PE stamping, would you accept an architect and their professional stamp?
We only do structural A's, S's.
Got it. Okay, good clarification.
Someone qualified for
Right.
B's, P's.
Right. Yeah. So I mean, it's a great point for new construction, and I believe that there are some nuancy ways. By the way, the answer to the question was architects only can only stamp structural on the residential side.
The architecturals and the structurals.
Architectural and structural.
Commercial architects can only do the architecturals. It has to be-
Got it. Okay, cool, thank you. So there are other ways to go about this, and I've talked to MEPs about this, PEs, other code officials, that as long as there's some good documentation that they can refer back to, and you can say, oh, well, if you're looking at let me see here. I'm gonna leave it here for a second. If the piece of equipment says it needs a 30 amp circuit, but we know that there's an 80% limit on that operation of that circuit for continuous power, we're going to take credit for that 24 amp, right? So we just saved 20% off of our load center in that logic right there alone, right? So as we go through and we start to look at details in NEC, I think that there is a defensible way through NEC to show a 100 amp panel being okay. And in fact, I'm going to be presenting on this in the spring at the ICC conference in Loveland. But there's a pathway through, and it really boils down to how many circuits you have and how they add up, right? There's only 5 circuits required in the residential, which is, well, there's the 5, and then there's the 220 amp for the kitchens, and there's all these other things. But when you really boil that down, you can get by comfortably on a 24 slot breaker box. But the question is, what are all the other things that these homeowners want? Oh, I want this, I want that, I want the other thing, right?
I'm having to put in a 50 amp car charger now. That's the code.
Is the code say 50?
I mean, technically it doesn't have to. I just have to provide the raceway, but I'm doing that.
Yeah. So I've looked at code references that reference 30 amp. I've seen it reference 40 amp, and maybe the adoption is 50 amp or the status quo. I don't know. But right. So the question is, 50 amp, are you counting it as 50 amp?
It's 40.
It's 40.
Charging that is 40.
Yeah, because it's a continuous load. Like demonstrably continuous load over 10, 12 hours or whatever. So is it fair to say we're going to count it as 40 continuous? We're getting nods. Sure, maybe. Back to a stamp, right? Okay. It really does fall back to the expectations that various people have along the way, right? What are the expectations of the homeowner? What are the expectations of the electrical installer, right? Of the builder and what their routines are? What you can get off the shelf in the local market? What are the expectations of the MEP that's going to be able to does the math and stamps it, and then the reviewer, et cetera, right? There's all these things, and everybody sort of, at a certain level, everybody has their own tolerance for extra, right? Somebody wants to round up and round up and round up and round up. And before you know it, your 600 amp panel, when we know that with a load shedding, demand management device like a span panel, you could easily handle that. I've shown it, I'll show it again. I don't have it on the slides, but anyway. I have one slide that I'll talk about it. I don't think it's in here. 400 amp panel in the Marshall Fire rebuild, like it's what had to happen. They have 3 panels, 3 like sub panels for different parts of the house. But those 3 panels are span panels. And we looked at 6 months of data, 6 months of data on it. The absolute worst 15 minutes was 99 amps. They could have handled that entire house comfortably with one span panel that could load shed easily up to sort of an equivalent 300 amp type of a service. And they were nowhere near the 400 that they were rated for. Right? Does that make sense? Okay. One more thing on here. This line right here, I've got this highlighted for a reason. 90% of max. That means that there are only 4 more 15-minute data periods over that 26 months that are within 90% of that 57 amps. So not only does it not happen, it almost always never happens, if that makes any sense whatsoever, right? Like this is 0.01% of the time is it within 90% of that peak. I mean, 50%, within 50% of the peak, only 4% of the time. 96% of the time, it is below 50%. Now, I understand that there are peaks and we need to engineer to handle these things, but this clearly states, or demonstrates, not states, demonstrates that this continuous load versus intermittent load thing is real and we don't need to design for absolute worst case. This is the watts at 50% of it's like a mean mode type of a play. It's like the average versus the most common. I apologize for the confusion on that. I like your detail though. Yeah. Now I'm gonna have to go look. I'm gonna have to get the answer to the question because it's a good question. Thank you for that. But yeah, those are based in watts. It's 3266 time periods out of 76,000. That's what it is.
Okay.
Yeah. Glad we got that. Glad we had that chat. All right. Moving on. A couple examples. Fraser gets pretty cold in Fraser, right? Fraser Flats, pretty cold. To be fair, these folks are not in the flats. They're up on the hillside up above. But they built a race car to win the solar decathlon, and they won the solar decathlon, if that makes any sense. It's a very cool house. The other one, I talked to Joe at a conference, a session I presented at, and he's like, yeah, mine operates at -30. Doesn't give off all the heat at -30. I definitely need more heat to supplement that capacity, but does the job. And he's had it installed for, I guess, going on 12 years now. Snow mass, warming hut on the left there. And we put that in as a test. Aspen Ski Co. wanted to try it out. Does it work? What do we got to do to decarbonize our building stock? And we're like, we talked about coverings and all sorts of stuff going on. I'm like, yeah, let's just put it on and see how it does. Well, it did great until they got 6 feet of snow in 9 days or whatever it was. 5 feet of snow, 5.5 feet of snow in 9 days. Facilities managers were overwhelmed with all the other snow. They didn't get up there to clean the snow off, and so it got caked in. So that is absolutely a real world scenario. If you get a huge dump for one of these, second homes in the middle of nowhere, do you stop having heat in this house? It's a fair concern. So I think there's some additional engineering controls, but you can see all this snow that's covered up on here, what they decided to do after the fact, and I don't think they've actually done it because they had other priorities come up, but they were going to re-roof this and bring it out just so it covered it, so that this cornice thing didn't get created with the blowing wind coming over the building. Does that make sense? And then one of the ski patrollers tried to help out and put his ice axe through the coil. And in a matter of 1 or 2 seconds, doubled his carbon footprint for the year. Don't clean them with the ice axe. Yeah, not a good idea. Defrost cycle. You were, Philip, you had a video of the defrost cycle on your laptop, on your tablet. Tell me more. Let's talk about defrost. Video, but you can see the frost, and you can see as it goes into defrost, it has these different bands of sort of connections and portions of the coil that it goes through, and those portions defrost at different rates. And so you're going to start to see water coming out. And I think Philip has a really good video that he can show that's local if you want to see more of that. But it just gives you an idea. But yeah, you have to plan for that water. I would not put that water near a walkway. I would not put that water near a driveway. I just let it drain to, I wouldn't even let it drain onto a solid surface, like pads.
See how that's on piers there? If you
Yeah.
can just do piers and not a slab,
Yeah.
and just provide some gravel bedding in there, you can probably, and slope it away from the wall, dwelling, whatever.
Yeah.
It'll mitigate it naturally. Especially if you place this on the south side, you're able to get this unit where it would get some sun jets.
Yeah. Well, so installer and inspector perspective wise, would it be, how fastened to the ground do you expect that outdoor unit to be?
It's down 115 miles per hour.
Okay.
We've actually seen.
You've seen them blown over?
I don't use pads. I always pour concrete.
You pour concrete.
And then I fasten the stand to the concrete.
Right. Yeah. And so, is it easier to just pour one concrete pad, or if there were, say, 2 strips. Like I think of like, if you were going to take a curb, right? Yeah, the tubes for sure. Pretty easy, right? An auger as opposed to sort of framing something up. Yeah. So finding an easy way to let the water drip to ground is my recommendation, because when the water goes to ground, it tends to dissipate more, right, as opposed to a slab area. Is that fair to say? Okay. So real quick on this, I'm trying to highlight, using that energy monitor, I'm trying to highlight what the defrost cycle looks like, right? So we've got this sort of point where it stops. It's that first check, or that first column there. And then you'll hear the compressor. So the system stops running. You'll hear the compressor, the reversing valve switches, right? And then the compressor ramps up and defrosts itself. It's sort of generating heat internally to defrost itself, runs it through the coil. It does steal some heat, a little bit of heat from the house, but that end-door unit coils are off as well. So there's a refrigerant loop. Go ahead.
Don't most of the hybrids have pan heaters?
Yeah, that's a separate piece.
Yeah.
Yeah. So this coil defrost is a function of fans off, compressor on, refrigerant circuit, defrosting all that.
The loop's running backwards.
The loop's running backwards. It's putting itself into air conditioning, but without any fans on. Yeah. And then once it sort of has this timeout, and different pieces of equipment will do that differently. Some of them are just based on time. Some of them are based on temperature. Mitsubishi's are adaptive. It's like, oh, how long since the last time I defrosted? How long did I have to run for that defrost until I saw certain numbers show up on my sensors and that kind of stuff? And so it learns and then forgets. So it's this adaptive cycle, which is another example of like different product quality that you'll have out there. You know, different cars have different engineering, you get different outcomes. But that's what keeps this defrost relatively short for Mitsubishi's, for example, and some others that are out there. And then some of them are like, it's 10 minutes, regardless of what's going on. And then it's like, it starts to really impact the amount of heat that it can deliver into the house over the hour of the design day. So all considerations.
What?
No, the refrigerant doesn't freeze.
Okay. I mean,
Yeah, no, fair question. The hydronic systems need glycol or some other sort of antifreeze in them. Those you don't want like staying, not moving when it's really cold out. That's a different deal. That's glycol. For the refrigerant, you don't need it. It doesn't freeze at all. But you might have that supplemental heat turn on during your defrost cycle. So for this 5-10 minute period right there, you might have supplemental heat heating the house, and that's a good design strategy. All right, so costs. Top line is electric resistance, propane, natural gas, and then heat pumps. The right-hand side is cost per millions of BTUs, right? So therm is 100,000 BTUs. A million BTUs is 10x, right? So what we might figure as $4.40 to run 1 therm's worth of electric resistance, which is expensive. We might figure $2.90 a therm or so for propane. Depends on the price you pay, what time of year, the efficiency that's going on. This is basically 100% efficient. I'm putting in 85 here because there's something about steady state and cycling of propane furnaces, etc. When a furnace turns on, it is not immediately at rated efficiency. It takes 5 to 10 minutes to come up to rated efficiency. So I'm using that 85 over the season. And by the way, this is different than sort of the bench test that you hear of AFUE, annual fuel utilization. This is closer to reality. So $2.90 for propane at $2.24 a gallon, and then natural gas, same efficiency, $1.23 a therm, about 16 cents $1.60 per therm, in that scenario for that 100,000 BTUs because we have a loss of efficiency. We're not running at 100% efficient, if that makes sense. Heat pumps are a different animal. It depends on the efficiency at what temperature, right? So we're very efficient. We're beating everything when it's moderate temperature outside. We're roughly a wash at 17 degrees in these scenarios. And I'm just estimating somewhere in between the 3.5 COP and 1.7. The 1.7 COP, when it's cold outside, is closer to propane. It's more expensive, right? And so that's when you start to think, well, what is my backup fuel energy source, right? How do I supplement when it's really cold outside, and thinking about those costs? So here, on the right-hand side, my January bills in Denver, it's not Summit County, it's Denver, 5 years running in January bills. My cost per therm went up 125%. And I'm just looking at my bill and I'm just doing the basic math and being like, oh, it's a lot more expensive these days. And you'll notice that it went up. So in that, remember when the war started over in Ukraine and energy costs went up? That's around here, right? And so we were paying higher prices because the US was exporting a lot more natural gas in the form of liquefied LNG, liquefied natural gas, to other places. And in fact, we can talk about that in a second. Then it went back down and then it went back up again. So these change. That's what this chart shows. The gray line is far more price volatile than the green line. Green line is electric. Yes, there's changes in price, but it's far less volatile. And my 20% increase electric rates versus 125% increase on natural gas. That's what I'm seeing in my house where I live. Other parts of the country are seeing very different scenarios.
Aren't you all electric at your house?
I just put in my heat pump water heater in the next month. So I had January is the last full, gas usage, and then my usage went to 0, and I didn't have anything to count. I put the slide back in, Jess. There's way too much on this slide. This is the crazy eye chart here. I want to point out a few key things. This is literally a snapshot of my utility bill. What I'm trying to get at is how much am I paying for my time of use energy versus opting out of time of use, right? That's the goal on this sheet. I'm in on time of use, and I have 3. This is that January bill, this past. And so I had 2,369 kilowatt hours amongst all 3. I added those up in dollars here. That goes in here. I divide it out. I get an average for that. I get a weighted average for that chunk, right? I am 8 cents per kilowatt hour on average for my time of use. Now I've got to account for my other charges and adding all this stuff up and backing out my $7.10 service and facility, because that's a fixed fee. It shouldn't relate to my variable costs. So I back that out. And now I'm coming in at 13.8 cents per kilowatt hour. I know that's crazy, but does it follow? Yeah. Actually, I think they went down.
For on peak?
I think on peak went from like 24 cents down to like 19 cents, or I don't know, something like that.
Right. It's like 20 cents.
Something like that. But and I don't want to get too in the weeds here. What I want to boil it down to on the bottom right-hand corner, time of use might save you money. It does for me. It does for a number of houses that I've looked at with friends. But I don't know what someone else's on-peak use would be. So if you use a lot of power on peak, it will cost you more, which is the point. It's supposed to.
That's the point.
That's the point. It is a pricing signal in the market to change behavior. That's what it's for, because Excel has very real costs that are extraordinarily higher that they have to compensate for, and thus they're capturing more dollars to compensate for it. So the question for the recording, the question is, how do you strategize your time of use with your heat pump, preheating or what have you? How do you strategize around that higher cost? Is that fair?
Yeah.
Yeah. I don't know.
Okay.
I don't know what it's like for that person. I don't know what else they have in the house. I don't know how they live in the house. Bake some cookies. I don't know. Like if you've got two things that you have to do, one of them happens to be like feeding your family. Am I going to pay a little bit of money for that while I'm giving off heat into my house? Sure. Let's do that. You know, if you want to set back the heat pump on your thermostat, maybe, but maybe you're just setting it back early. Maybe you're preheating in the middle of the day so that all that mass that is the house, and there's a couple strategies around that, but heat up that 200,000 pounds that is your house, or 400,000 pounds that is your house, inside the thermal envelope, so that it can coast through until you go to bed, and then let the temperature drift at that point. But heat pumps fundamentally are designed to set it and forget it, right? So they charge the system up, they heat everything up, and then they maintain. And so they're automatically using less power during that, when you're sort of in that coast mode. And when you're arriving home from work, or maybe you work from home or whatever, but you've got people there, you're cooking, you're cleaning, you're turning on TVs and whatever, computers, whatever the stuff that's going on, everybody's there. I typically see the heat load even though it's getting colder and the sun's setting, I see the heat load actually drop because your internal gains are higher. You've got a greater offset automatically, probably to the tune of 3,000, 4,000, 5,000 BTUs, and if you're cooking a lot, it could be double that, if that helps. Okay. All right, design requirements.
They could use.
It makes sense that they do. I have, with my EV, they can send signals on when not to charge. And so I've signed up, WeaveGrid is their program implementer for that smart home charging thing. And so I opt in to say, I want to avoid high rates, and I want to optimize around renewables. That's my choice. And so I'll see a prompt to say, oh, your car is going to start charging at 11:15 p.m. and then it's going to charge for 2 hours, and then it's going to be off for 2 hours, and then it's going to be back on, and so it's going to get you back to 80% by 6 a.m., which is my ask. I say, I want these priorities, avoid peak rates, and prioritize renewables, and I want it at 80% by 6 a.m. And then it does the math. And that keeps me charging at that 8 cents per kilowatt hour, which is so cost effective compared to paying for gasoline. Like the cost to run my vehicle is a fraction of gasoline. I will never go back, just for that alone.
$3.30 to drive 100 miles is what my car is.
$3.30 to drive 100 miles. Yeah, so that's 3.3 cents per mile. And if you compare that to the federal reimbursement rate, right, on your taxes, 57.5 cents, right? And oh, by the way, you don't have oil changes, et cetera, and so on that are, it's a ridiculous, value proposition. So design requirements, manual JSD. The manual D is for ductwork. I know we're hydronic mostly here, but manual J is still the design paradigm for hydronic. Manual S is still the selection paradigm for hydronic. So the goal with manual J, manual S is to look at sizing, You want to avoid too small, you want to avoid too big, you want to look for that just right, the Goldilocks principle. There are reasons, mechanical, operational, comfort reasons to stay away from too big and too small and go for just right. But the question is, what is just right? Plus or minus what, right? And that's up to the designer, it's up to the builder, it's up to the homeowner, and it's up to the programmatic requirements as well. There are limitations on that in Manual S, for example. So this demonstrates, block load. That's the whole house all together, and you can get one system to cover the whole house as long as you're distributing to proper locations. The right-hand side is room by room, which is sort of that typical Manual D approach or Manual Z approach, which is zoning with ductwork and that kind of stuff, and emitters, right? Hydronic. What is the manual for hydronic? There's another one that I'm totally missing right now. There's like a half a dozen of these things, and we only talk about Manual JSD generally. But in the middle is really that zoning, that Manual ZR, I think. And that's taking care of one part of the house versus another part of the house, not just room by room. And I think that's where we're going to start to see a lot of design parameters, or design strategies spend most of their time. Certainly on the multi-zone heat pump arena, for sure. There are tools that are out there from different manufacturers. Some of them are just spreadsheets. This one happens to be from Mitsubishi, and there are some other manufacturers that do, like Daikin, I think has something similar. LG has something similar. Carrier, I think, has something similar to this. And the goal is to lay out the system so you've got your outdoor, you've got your indoors, and then you've got your zone capacities, if you will, and then you check these numbers against your load calc, right? This is part of your Manual S selection process, just making sure that's 12,500 BTUs is enough to cover that mud powder second floor zone, etc. But also in here is the charge of refrigerant. How much additional refrigerant might we need for that system? Well, in this system, the additional refrigerant is 8.53 pounds additional refrigerant to run this overall system. Basically because this doesn't ship with all the stuff in it. If you've got a one-to-one, like a monoblock, like a hydronic monoblock, which we'll see in a minute, it's going to have all the refrigerant on board. You're not going to have to add anything additional. You're just adding water or with the glycol or some other antifreeze into the loop. There's also the design conditions. So these numbers are by design for the conditions up here. It's altitude. And in fact, these D rates right here, these correction factors, this deals with temperature, piping length, defrost cycling, and what you don't see in here is actually buried in this 0.68 D rate is altitude as well, right? So it does all the math for you properly, because doing that longhand is a pain in the butt. I don't want to do that, no one. So we think about double checking the specs on the equipment. We use these design parameters, but we have to pick the right pieces of equipment, the right model numbers. These two pieces of equipment are 1 to 2 digits off on the model number. They're really close. It's easy to miss. The top one is 100% capacity at -13. That's what new equipment is capable of. It will deliver 100% rated capacity at -13. It's getting better and better and better. And really good minimum turndowns, so in the spring and the fall when you have part load conditions, you've got good operational efficiency. This other one that is a couple digits off needs a lot of supplemental. This right here, improperly installed or selected and installed, this upsets people a lot, right? This is what gets the builder in trouble, the installer in trouble, the code official for saying, yes, this is okay. This is why they ask for this information to say, yes, this looks right to me. And there's some fairly easy ways to look at this stuff. Yeah, I thought I had another slide in there. I apologize. looking at this capability out of NEAP, number one, just the number one item, make sure that there is a -13 number on this chart. That's the minimum heating minimum capacity. This is the heating capacity.
What's the number of the -13?
Oh, it's, I don't know, 2,000.
Like zero.
Close to zero. Yeah. I mean, it's just running. It's just like just barely chugging along, delivering a little bit of heat. But irrelevant, really. Like, because our slope, remember our demand, our load calc load, our heating load slope looks like this. So we want to make sure that at our design condition, we're at or very near 100% covered, which is why having not only 100% at 5 is so important, but having this guy up here as well, right? And operation down to -20 whatever. This is Yaddle run down to -13, but you need a lot of extra supplemental heat to cover that. You're going to be paying a lot more, not only in the balance of system, the extra system to do it, but the additional less efficient cost. Does that make sense? So number one, make sure you have a -13 number on the NEAP chart. Number two, that they actually do the manual J and manual S, and that the software demonstrates that each zone or the overall meets the capacity. Those two things alone, at your design conditions, those two things alone will avoid most of the issues going in. Any other thoughts from the installer? Oh, that they turn off. No, this guy is guaranteed operation down to -24. This is the new 454B version. Yeah. So the -13 it's just a number it's a tested number. That's why they talk about -13, by the way. It's the same thing as -25 Celsius. It's just a number that the world tests equipment at. So it's just a number that they picked. The operation guaranteed, this will operate guaranteed at -24, and I've watched them operate at -29, -30. But yes, that -13 is a consideration for some equipment, absolutely. So finding the right spec, double checking the spec. Ooh. Oh geez. Quick version. The red line is that capable system, a little bit of supplemental. The gray line is a competitive system, two of them, that stops operating as I forgot your name. Seth. That Seth talked about. It turns off here, which means you need backup for everything else. You need an entire separate system to heat the house. This red line supplemental system here, right here, 3 kW heat strip. That's all it needs for supplemental. All in, 65 amps of breakers on that outdoor panel, on that load center. This doubled up system with 18 kW backup, 190 amps of breakers. This is where we start to get into 300 and 400 amp systems. Not great. All right, let's get into hydronics specifically. They're not yet rated in the US, according to AHRI, American Heating and Refrigeration Institute. It's coming soon. When that shows up, that means you're going to start to see those qualifying for incentives regularly. You're going to see better documentation like we just looked at before. You're going to see a lot more uptake in this market for sure. Availability of the equipment, being stocked, etc. This is a fun, this is a great article, by the way. If you have a chance, go check out this article. You got to get a free login account or whatever. But that JLC article is really quite good. And it talks about specifically air-to-water heat pumps. So check that one out. That link should stay live when we share the PDF. This product here, Mitsubishi, Daikin, others are bringing product in from Europe. And they're going to be able to do magic things, right? This literally is this sort of magic box. It does a bunch of stuff in the box. Hot water, space heating, and cooling, in-floor heat, low temp radiators, convectors. There's all sorts of capabilities around that. You might have to swap out that 150, 180 degree radiator, whatever, with something that's more efficient, basically effectively double the area, something along those lines, twice the length or maybe just twice as high, but more of a European style convector. Looking at the systems are highly efficient, but you've got to double check the specs. So because we don't have that one chart, here I pulled up the performance chart of a particular model, a very good model, but you can see it definitely drops, right? And so this is 95 degree water as it leaves the unit, and this is 130 degree water as it leaves the unit. This system is needing to deliver hotter water to the house or to whatever. But you're not going to get as much out of it at these low temperatures, negative 13, negative 20, etc., right? So that's where your supplemental is going to be showing up in there, right? But it will operate down that low. You just got to have that supplemental. So an inline resistive heater, etc. This chart is about the antifreeze D-rate, a correction factor. So the more antifreeze that you have, in fact, there was another chart I was going to try to tuck in here. The colder it gets, the more antifreeze you have to put into the water. And the more antifreeze you put into the water, the more of a D-rate you have. So these are different types of antifreeze, and this is the percentage of antifreeze by weight. So if you're having to put in 30% antifreeze, you're going to take a 2 or 3 or 4% D-rate on capacity. It's there. It's not a lot, but it's part of the details to be designed. So some best practices: avoid the drip line, avoid snow slides, raise the unit up, let the water drip to the ground is my opinion. A well-designed concrete pad is great for sure, but just making sure that the water sheds off into an area, it's not going to be a problem. Noise and vibration, let those lines stay a little bit slack, not directly into the house, right? When that line goes 1 foot right into the back of the house into a framed wall, you're going to get some vibration. It's going to transfer that vibration into the house. So in the same way, it's a weird analogy, garden hose. If the garden hose is straight, you can sort of flip it and move it, right? But if that garden hose goes around a corner, if it turns, it's hard to flip it to get it to move the second half of the leg, right? If that turn shows up in the line set, it's going to help absorb that vibration from the compressor and those fans into the house. Does that make sense? Okay. Animal protection, making sure that the backs of these have access panels back in there. Just make sure that those are intact as well as you can. Tape them off, screen them off, do something like that. You don't want field mice or whatever getting into those and chewing on wires and making a nest on top of the compressor that's maybe been off all summer, but it's because it's a nice cushy spot and it's full of wool that insulates the compressor. Bad idea. You go to start it up when you really need it, you got nothing. Key point. Don't oversize a standard heat pump and try to get it to perform like a regular cold climate heat pump. It's not the same thing. In the same way that you're not going to just put snow tires on a front-wheel drive car and get the same performance as all-wheel drive with studded tires and anti-lock brakes, traction control, et cetera, and so on. It's a very different engineered system, right? If you're driving up here, you probably want some kind of decent all-wheel drive as opposed to getting by with bad tires and not great traction. All right. Operational issues we've had with the recent cold snap were due to our design or installation issues. It's not the equipment's fault. This is one of the best technicians I can think of. They install thousands of heat pumps in Boston, in Colorado, and now in California. They deal with customers across the spectrum, cold, hot, whatever. Design for the conditions you're going for, follow the specs, and you will get, and with good product, not perfect product, good product, you'll get the outcome they've been engineered for. Heat pump contractor resources, some great lists here. Let me know if there's anything on here you want me to take off, Jess. There's some good folks, some good information, and some good resources. All right, so some closing thoughts. From 1935 to 1950, 15 years, we went from 10% of the United States farms electrified to 80%. So we ran electrical grid across the vast majority of the United States in 15 years and brought power to farms. That was the Rural Electric Administration's move. What else did we do during that time frame? We fought a world war on two fronts, right? Blood and treasure. A lot of work. Both things were a lot of work, right? I think that we can do this electrification thing. From 1950 to 1995, we 10x'd power grid. In 45 years, we 10x'd the power grid. Now, we're at a particularly painful, pivotal, critical point right now. We got to solve a lot of things. We got to figure out a lot of things. We got to figure out where we're going and how to get there together. But we're not talking about 10x'ing the grid. We might be talking about doubling the grid. And a lot of estimates that I'm seeing, I think we can get by at 30 to 40 to 50% larger than what we do. But we need good design, particularly with data centers, particularly with vehicle chargers, particularly with planned developments, et cetera, and thinking in a two-way mindset. Power flows, electricity flows in two directions. We got to stop thinking one-way power flow. We got to start thinking two-way power management. And this is how we get there. So we've talked about a lot of these things already. If there's any remaining questions, please let me know.
I'm going to throw in a plug here. If you're considering going all electric for a new construction home, make sure to check out Xcel Energy's residential new construction program for rebates up to $25,000 for a home that exceeds the building code and includes all electric heating and appliances. Go to xcelenergy.com and learn more.